So good morning, everyone. Welcome back to NPTEL live session for week 2. So sorry for the inconvenience that we are starting at 10 a.m. today due to some logistics reasons that we cannot skip this meeting. So we will wait for a few more minutes for others to join and then we can start with our week 2 session. Thank you for joining. Okay, so we can start now. So last lecture that we ended up was with the cyclopropynyl cation ligand. So we'll just take a recap of that. So topics that are going to be covered today. We'll still take C3R3 as a ligand and its reactions. Then we will start the topic of cyclobutadiene as a ligand, which is C4H4 system. Its preparation, and there are a lot of preparations of it. So we will be taking into its preparations. Followed by that, we will be talking about the structure and bonding. in C4H4 transition metal complexes. Followed by that, we will see the reactivity of we'll see how these complexes react. Reactivity of transition metal C4H4 complexes. So here Tm is transition metal. Followed by that, we will be having C5H5 as a ligand, which is your CP ligand, and full name is cyclopentadiene. So we will take up its examples. Then we will talk about the preparation, followed by we will see the molecular orbitals and their properties. So this is for today's session, and at last we will be talking about the problems, right? So let's start the topic with C3R3 positive, which we ended up last time. So you already know that. So first is C3R3 positive as a ligand. So this particular ligand is aromatic in nature, as it obeys Huckel's rule, where 4n pi n plus 2 pi electrons and n is equals to 0, so total becomes 2 electrons. And this has been first synthesized in 1957 by Breslow. Now, for the examples, we have one example where when we are taking this system, P3, PH3, C3, Br, meaning this is positive, having pH, 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 and Br negative is outside, having double bond. And when it is treated with nickel CO whole 4, where nickel is in 0 oxidation state, then it's a kind of oxidative addition where nickel goes from 0 to +2 state, and we end up having nickel binding with both Br as well as cyclopropyl group, pH, pH, and pH. And here one carbonyl would be there. Again, Br is in the bridging mode, and it would bind with the nickel, next nickel with CO, and having the symmetrical structure, pH, pH, and pH. Right? So this is the one of examples where the C3PR3 ligand will react and it would bind with your transition metal. Now, another example that we have is, take the next slide. Example 2. So when we are taking the system, this is pyridine and it is bound with pyridine and bromine. And the fourth bond is with the C3P3PH3 ligand, right? So if you will see carefully, pyridine is this one, where lone pairs are attacking onto the nickel. So pyridine is a 2 electron donor. So 2 is coming from pyridine 1, then 2 is coming from pyridine 2. 2 electron, 2 electron, 1 electron. Right? And when this reacts with thallium Cp in benzene at RT, so it forms this 5 ligands will be replaced by Cp because Cp will give you 5 electrons and rest other things would be same. Here, the distance of nickel carbon bond is 196 picometer and distance of CC bond is 143 picometer. Now moving ahead, this was it for the C3R3 positive systems. Now we have second topic is for the C4H4 cyclobutadiene as a ligand. So firstly, we'll see the preparation. So its preparation is from dehalogenation of dihalocyclobutane. So we have this is a substituted dihalocyclobutene. One bond is there, so it is butene, 2 halogens. So this bond will come inside and this chlorine will release. And since we have nickel CO4 here, so nickel, this goes and ultimately it reacts with your nickel, releasing the nickel chloride, and you will be having, because then it would form a structure like this way. Right? So now it becomes a cyclobutadiene ligand and it can interact with your nickel center. So how it will interact? It would bind at one side and the rest chlorines, they can act as a bridging ligand, forming with the other nickel, thereby balancing the whole charge and total valence electrons. Right? And here we have, in this particular thing, here we have distance of or bond length of nickel carbon is 199 to 205 picometer, and the carbon that means distance between two carbons is 140 to 145 picometer. This lies in a range of double bond sp2 hybridization. So these are air stable and red violet color crystals that are formed when it is being treated with dihalocyclobutene. So this is one such example. Now we'll see the preparation of dihalocyclobutadiene cyclobutadiene based transition metal complexes. So our next thing is preparation method. So we are doing the preparation. The way we talked about earlier, dehalogenation of dihalocyclobutene. So we are taking a dihalocyclobutene, where we are having two cyclo. So this is called as dihalo because of two chlorides. The nomenclature would be two dichloride, dichloro, cyclobutadiene, because there is one bond. Now when it is treated with Fe2CO9, so this is a dimeric structure where two Fe's are there and 9 carbonyl groups are there. We know that in this kind of reaction, the Cls will go out and there would be a formation of one double bond and the loss of FeCl2. The other Fe will be making a bond with the cyclobutadiene, and for completing the valency, we will be having 3 COs. So here also it follows 18 valence electron. Now if you calculate, your cyclobutadiene gives you 4 electrons. Iron is 26 atomic number, that means 3d6 4s2. So total electron contribution is 8. 2 electrons are coming from CO, 2 from CO, and 2 from CO. Total you have is 12 electrons from here, plus 6 electrons, that is 18 electrons. So this is a stable complex. And here also, you need to say this is a planar ring. Therefore, the DCC bond is 146 picometer. Melting point of this particular system is 26 degrees. That means it will melt at room temperature itself. And the structure is diamagnetic. So that is an important feature for this particular complex. Now we move ahead with the next preparation method. So next preparation method is from the dimerization of alkynes. So from dimerization of alkynes also we can produce a cyclobutadiene based transition metal complex. So what we have is, we are taking a salt Na2 palladium Cl4.
बेटा चाय ले बे जूठा कर ले बे
Hello.
कितना चाय दोगे अरे छोड़े ला सोचा है बेटा
Can you please
सोचे
mute
करी
yourself? Thank you. So Na2 palladium Cl4, when it is being treated with 2 molecules of alkyne, this bond is referring to the alkyne bond, and in medium of ethanol. So here if you'll see, this is palladium in +2 state, and we are having an alkyne and it is being given ethanol in medium. So how this particular system would go into dimerization? So generally, what happens when we have PHC triple bond CH and we are taking 2 molecules, this one bond goes and bind with our carbon, and again, since the charge increases, this goes and binds here. Ultimately, it would give you C double bond. If I'll name it 1, 2, 3, and 4. So we have 1, 2. Now one bond would be between C and 2, and another bond would be between C1 and C4, and rest pH would be as it is. So this is nothing but your cyclobutadiene system, right? Now, there is also one possibility that even if we are saying dimerization, this particular system, when we have C triple bond CPH, it can also go to trimerization. So we have right. So this way, then this way, and this way. So ultimately it would give you a substituted benzene ring with all over phenyl groups. But this particular group is not an active ligand, whereas this would come as your side product in these reactions, and the formed cyclobutadiene will react with your palladium, and ultimately the products that you will get is the palladium was there, and we know that it would undergo dimerization with the cyclobutadiene ligand. There was pH, 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 and pH, and one Cl here, another Cls would go into bridging and forming the same thing with the other palladium, right? So it's the same system that we saw with nickel also earlier. And the side product would be this benzene, substituted benzene group also. So this is a kind of reaction which we got from the dimerization of the alkynes. Now, what would happen if we are having a, now next method if you are taking, the method is called preparation by ligand transfer. That means if we already have a transition metal complex with the cyclobutadiene, and if you are treating with that complex with some other transition metal salt, would that be transferring the ligand or not? Let's see. So if we have the same complex that we just made, the cyclobutadiene one, and having a bromine instead of chlorine, we are taking bromine, and so on, right? So now here I'm doing R and R, where R is equals to pH. Same thing here also. Now I'm treating it with same Fe2CO whole 9. So what would be happening? Since I said that it's a 18 valence electron, so it would be maintaining its 18 valence electron, and it will only take the cyclobutadiene ring from here, and the rest would be its coordination with the carbonyl group, and this becomes an 18 valence system. So here from one system, the ligand has been transferred to the other metal. So this is also one process of preparing transition metal complex with cyclobutadiene. Another method is by ring contraction. Of metilla cyclopentadienes. So what is that? So cyclopentadiene meaning cyclic ring should be there. Penta meaning 5, 1, 2, 3, 4, and fifth center, which is the metal. That's why it is metilla cyclopentadiene. So we'll make the double bonds here. And if it is having a substitution, we'll give a substitution here. So it's having a substitution of pH, and tin is having methyl substitution. Now, when it is being treated with nickel bromide, it undergoes a ring contraction. That means this bond would go and bind, attack with this one, and this SN releases. And when SN releases, SN Ne whole twice, that would release out. And when this forms a cyclic group, cyclopentadiene, then we have nickel bromide in nature, and again it would end up forming nickel, bromine, bromine in, and this would be a dimeric structure again. So whatever the stable possibility is there, formation of a stable product, it would ultimately end up forming that. So therefore, here we saw that 5-membered ring is a contracting to making a 4-membered ring. That's why it's called as ring contraction. And the side product is your SN Ne whole 2. And when the ligand has been released, it would react with your nickel and forming a dimeric structure. Similarly, in another example of ring contraction, if we are taking, instead of tin, we are taking aluminium, Ph. There is a ethyl group, and this is an ethyl group, this is a phenyl group. So in presence of lithium and nickel bromide, since we are adding alkali metal, it would reduce it. And therefore, ultimately, there would be a ring contraction and this would release, and we will be able to have. Now, here in presence of the lithium, it would try to make it a monomeric structure having both groups similarly attached. That means cyclobutadiene groups every side. Right? So this is a first binary structure, cyclobutadiene complex, given by Hauberg in 1978. So I hope this is clear. If there is any doubt, please feel free to unmute yourself and ask the question or put your question in the chat box. I'll be happy to answer your question. Otherwise, we'll move ahead with the structure and bonding of cyclobutadiene. So just giving a recap that in case of cyclobutadiene preparation, we have seen following methods. One method was dehalogenation from dihalo cyclobutene group, right? Say, for example, if you have something like this way and you have chlorobromoiod or whatever the group is there, that would release out, and this bond that would form a cyclobutadiene. Second preparation that we had was dimerization of alkynes. So as I said, they just don't dimerize it. There is also a possibility of trimerization. And if you have, so ultimately, say C triple bond CR is there, it would be giving you a cyclobutadiene group along with a substituted benzene ring, which would come as a side product. The third method that we saw was the ring contraction. Meaning, if you have a 5-membered ring, so if you have a 5-membered ring where 4 are your carbon centers, 5th is your metal center, though it is named as metilla, cyclo, penta, diene, where 2 double bonds are there. And once the ring contraction happens, meaning it would try to bind with this one and this releases, and ultimately you will get a cyclopentabutadiene releasing your SN-Me group, and similarly with the aluminium also. So these are the 3 main methods for making a transition metal complex with cyclobutadiene that we have taken into consideration. Is there any doubt so far? If not, then we can move ahead with the reactivity part. So reactivity of transition metal cyclobutadiene complexes. So these cyclobutadiene complexes, these are aromatic in nature, and therefore, so like aromatic compounds, you have already might have read in the organic chemistry, they also go electrophilic substitution reactions. So if I'm taking a complex, transition metal complex with cyclobutadiene, this we have already seen the preparation. It's an 18 valence electron. Now I'm treating it with CH3COCl in presence of a Lewis acid, which is AlCl3. We already know in case of benzene, CH3CO will go and attack onto this one. So firstly, it would form a intermediate where one H is here and CH3 here, C double bond O, CH3 would be forming, giving a positive charge to whole complex. Because this electrophile has been attacked by the double bond of your carbon and carbon. Once this is there, it would release H positive. That means replacing, substitution meaning this CH3CO, the positive electrophile, would be replaced by the proton. The proton would go out and you will get a C double bond O CH3 reacting onto that. And ultimately you will be having Fe, cyclobutadiene, carbonyl group. And here we said that it was C double bond O CH3, right? So this is the way where we will be having electrophilic substitution from our group. Now, we will talk about the structure and bonding. So in structure and bonding, first thing first, we'll make the orbitals. So these are the ligand orbitals. So here, all symmetrical. So it will form sigma. Then we have these orbitals where this one, four MOs we have in hand. And the last one, the diagonals, lobes. So this category, this is pi, these are deltas, and this is sigma. And this was with the ligand. Now we will be seeing the metal, which metal orbitals would participate in making this sigma pi or delta bonding. So in metal, the s orbital, pz orbital, and dz square orbital along with the z direction. In pi bonding, we have here px, dxz, or with this one, py, dyz, and this one would be formed with the dx square, y square of the transition metal, right? So some features are there that pre cyclobutadiene is rectangular, whereas in transition metal cyclobutadiene, complexes, it is square. Planarity comes and it becomes a square. So the distances, the angles are 90 degrees and distances are equal. Now moving ahead with our next topic, which is cyclo C5H5 as a ligand, which is cyclopentadiene ligand, called as Cp minus. So firstly, we'll take the examples. C5H6, what we have in hand here, there would be two hydrogens. If it has been treated with potassium, this is a metal. It would take up one electron. It would give one electron and form K positive. Once this gives an electron, this H is going out, and therefore one would go as a H positive. One another H that we get is take an electron from potassium and therefore releases a hydrogen gas. So we ultimately get K plus H C5H5 minus, followed by some examples. If we treat two molecules of C5H6 with iron at a temperature of 300 degrees in presence of aluminium and molybdenum oxides, it would form C5H5 twice iron and hydrogen. So this is your iron Cp sandwich group. Another examples, if we treat a C5H5 magnesium bromide, which is a Grignard reagent, so here it is +2 minus and this minus, and treating it with Lewis acid iron chloride, it would form stable C5H5 twice iron, and it would release one molecule of half a molecule of C10H10 and 3 molecules of MgBrCl, right? Another topic that we have is these C5H5 transition metal complexes. They have a double cone structure, specifically if they are forming like this way, right? So the sandwich complexes, meaning if we have a FeCp whole twice, so this is a sandwich structure. It is having no magnetic properties because it is diamagnetic. And since it is diamagnetic, dipole moment is 0. Whatever the dipole is this side, it is getting cancelled from the other side. So if we have how to prepare the reagent, let's see. So we have H over here. So at 100 degrees Celsius, if you will carefully see, this is 1, 2, 3, 4, and 5. And these are also 1, 2, 3, 4, and 5. And in presence of at this degrees, it can easily release a proton from here and proton from here. It would release your, it would break the bond, and therefore you will end up having two groups with the H and H, right? So this bond is actually breaking. These bonds are breaking. And when this is being treated with sodium, it would form two Na positive and CH5H5 negative plus a molecule of hydrogen gas. So this is basically a thermal cracking. So it is actually a retro Diels-Alder reaction, where we know na ki we have a 2 plus 2, 2 plus 4 Diels-Alder reaction. It's a retro. Here we are breaking. There is what we make a cyclic group. So here the deprotonation happens in presence of strong bases. And NaCP is the most common reagent that we use for making the transition metal complexes for with the C5H5. So now we will start with the preparation. In preparation, we have a metal salt, metal chloride, and when we are treating it with two molecules of NaC5H5, it would form C5H5 twice metal. Here the metal would be vanadium, chromium, manganese, iron, cobalt. And solvent that we will use is THF, DME, NH3, etc. If we are having nickel ACAD and we are treating with C5H5 MgBr, this is the Grignard region, and it also will form C5H5 nickel plus two molecules of ACAD with MgBr, right? Moving ahead from different examples where we are taking, so I'll take into the consideration like preparation. Now, if we generally have a tantalum chloride with NaC5H5, it would give you eta 5 C5H5 with tantalum chloride. And again, if you treat with excess amount, so what really happens, one molecule is C5H5, eta 5, hapticity is 5, another would be having eta 1. This is a vanadium group, but a 5 element. So if we are having, so one will make a sigma bond, other would make a pi bonds also. And if you're treating with rhenium chloride, so in these cases, it would end up making a eta 5 C5H5 and a hydride bond as well. So the reactions with, so the thumb rule is so the deco message is the reaction of NaCP, which is Na positive, C5H5 negative with 4D and 5D salts. Often gives Cp metal hydride complexes or sigma bonded, which is eta 1 Cp complexes instead of the sandwich Cp2 metal complexes. So this is very important that you need to remember. Do not end up having the Cp2M complexes, and with 45V, the reactivity is different. Now we'll take the different preparations. Okay. So here, firstly, we have M metal with C5H6. It would form C5H5 plus half a molecule of H2. If our metal is lithium, sodium, potassium. Second, if you are treating the metal with two groups, then it would form at 500 degrees Celsius. It would form 2 plus H2 release. And here the metal has to be magnesium or iron. Meaning here the less electropositive metals, they react only at high temperatures Now, continuing with the metal salt and cyclopentadiene system. So we have we take a phosphine group which is bound with copper and a tertiary butoxide. The copper is in +1 state. Then we are treating it with C5H6. So it would have since it's like electropositive, would have this molecule, and PET3 is still there with oxide. Tertiary butoxide would take up the hydrogen proton, followed by if you are treating in presence of base. So here above we didn't add the base, here was already having the base inside. So if you are treating in presence of base, say for example iron chloride, 2 molecules of C5H6 and 2 molecules of diethylamine, it would form C5H5 to iron, plus the amine would take your NH2 and form a complex with chloride, right? So sometimes we need to additionally add the base if basicity of salt and iron is insufficient. Now the next is molecular orbitals. Properties. So here we have a little different meaning. Since 5 atoms are there, so 5 molecular orbitals will be having. The first one that we have is symmetrical lobes. So this would form sigma bond, but it is called as A bond. Then we have two above, two down lobes, and here come as two above and three down. So these two comes in a category of E1. And this one is, so here earlier was two same side, now they are in opposite side. And here also we have two above, this one is above, and this is comes in a category of E2 microorbital. So these have been formed from salic. Sorry. So salic is your symmetry adapted linear combination of atomic orbitals to give you molecular orbitals. So this is bit quantum, so we are not going into depth of it. So what are uh, the metal, how the metal is going to form it? So this one, the other ones, rest sigma and pi, we know, like this would form sigma, this would form pi, and this would end up forming a E2G would form a delta bonding. So how it forms with the transition metal complexes? So we have delta